Hey, hi everyone, this is Vivek and welcome to the day 4 of the DP workshop. In this particular day, we're going to talk about some different miscellaneous ideas that you would find very interesting. And these would be interesting state ideas, interesting optimizations, maybe that would help you in many more problems. The first thing that we're going to take up is this LIS in nlogn. So this is a very interesting like optimization that happens to be existing for LIS. We had talked about LIS in one of the in n square in one of the previous videos, but in this video we're going to drop it down to order nlogn, and this is one sub problem that is asked in many problems. Okay, so never skip this particular one. Okay, also apart from just finding it on nlogn, we can also talk about how to print the solution in nlogn, which is I think many people skip out. So we're going to talk about that too. So what is the basic LIS idea? Essentially, in LIS, you need to find the longest increasing subsequence. What is a subsequence which is increasing in its value? So in this case, what is the longest one that I can find? Maybe 1, okay, 5, you can see 6, 8, 9. That's the longest increasing subsequence that we can kind of look at. And in this case, we did happen to had discussed a brief O of n square idea that could have been used for this one, which did something like this, that dp of a certain level was equal to the best LIS ending at level. And then what we did was, like, if you are at a particular level and this is where you want to find dp value of it, you're going to be going over a previous thing and finding the best thing and best ending over there, and possibly extend it with just a single connect, right? In case this value is going to be less than this value, then you can connect them up. So we had a transition like this, that dp of level is going to be equal to, let's say, max over all different j's, such that j is less than level and is greater than equal to 0, right? Any previous index than any particular level. And for all the previous indexes, we're going to find out max of dp of, for the previous index j, plus 1. So there is a subsequence that is ending at j plus 1, provided that we can extend it. So the condition to extend it is going to be ARR of j should be less than ARR of I, right? That's the main condition. So that's the basic DP that we learned. This was nothing but a form 2 formulation, right? This was a form 2 formulation. And this is O of n square. This is an O of n square because the state is O of n and the transition is going to be O of n as well. Now what we're going to deal with is how do we optimize this even further. Okay, so how do we improve on this? The first thing that we need to think about is, what is the way to generate the subsequences? Like, is there any other way in which we can generate the subsequence, or how do we optimize this? And we come to this notion of incremental processing, right? So let's say we have a set 1, 5, 7, 10, 9, right? So till this point, the only subsequence that is possible is 1. Then again, if you include 5 into this thing, the way you can generate the longest increasing subsequence is either you keep 5 itself or you append 5 at the back of 1, right? Okay, then for 7, you can either you extend something that was already created over here in this collection. You can add 1, 7, okay? You can add 5, 7, okay? You can add 1, 5, 7. These are all possible increasing subsequences that are there, right? At this part, you can see that for 9, you can extend anything over here, 1, 7, 9 or 1, 5, 7, 9, right? These are different subsequences that are currently getting formed. So we are not going to create the sets or the subsequences that we are writing over here, but let's say we kind of deal in our mind with this notion that at a particular index, okay, what are the different subsequences that has been generated till that point? And if you get a new element a, it's going to be something like we try to append a at the back of everything. Something like that is going to happen, right? So this is called incremental processing, where we have built certain set or certain partial solution for whatever we have till this index, and then we extend the solution, partial solution, by one more element getting added to the set. So it's incrementally building the partial solution that is getting processed, right? As you add 9, you get an incremental solution, which is going to include all the previous solutions, all the previous subsequences, and the one that got generated by 9 as well. So this is called incremental processing, that you first find out till this much, then you include one more answer, one more number, and find for that what is the incremental changes. then for the next element, what is the incremental changes, and so on, right? In fact, in form 2, we also did something incremental, right? If you go back, like first we find out the answer for this much, and then for this one we need the answer for the previous fuse, right? So it is also incremental in some sense, right? But yeah, this is more like a general incremental idea that we have to keep generating subsequences in an increasing fashion, with more elements getting added one by one, and the way the new element behaves is something specific to the problem. In this case, is going to append at the end of the subsequence and extend it if possible, right? So that's called incremental processing, and we will try to see how we can use this one for this particular problem. Okay, so once we are done with this, we need to talk about comparing partial solutions, right? So think about different subsequences that are currently getting generated, right? Let's say there is a subsequence of some chain like 1, 5, 7, 10, right? And let's say there is a subsequence of 1, 5, 10. These are both valid subsequences. Let's say you are incrementally building the answers at any particular point in time. We will think about what are the different subsequences that are feasible. One is 1, 5, 7, 10. Okay. Other is 1, 5, 10. Which one do you think would be relevant for our solution and which one would not be? I mean, going forward, if you append new elements one by one, even after that, is there any point in keeping this one provided that this is present? Is this like even making any sense to keep this particular thing available now, or maybe try and extend it up if this is available? No, right? Because if you extend beyond 10, right, if you already have a 4 length subsequence, then it's always better to extend it with that one instead of having a 3 length one, because this will give us the max length, right? So we first of all understand that if we have two things ending at the same value, one with the bigger length is one that we should keep, right? We should never keep, like, if they are ending at the same value, what is the, let's say, the second most best or third most best or whatever the length is, right? So these lengths would not be relevant because the max will be generated by the max ending at that value. Okay. Next is, let's say we have 1, 2, 3 as a subsequence at a particular place, and 1, 5, 9. Okay. So till this much, these were the two sets that were generated. It's not for this particular example, but let's say these were the two sets that were generated. Out of these two sets, which one do you think we should keep and which one do you think we should eliminate? Okay, because if you keep all the incremental processings, potentially there can be 2 to the power n number of subsequences, right? Because every time you add element for all the things that were there, it can be potentially copied the same way, or it can be added with the new element. So every time it is doubling. So the number of subsequences is actually 2 to the power n. But we want to try and prune down which ones are actually relevant to find the maximum LIS, right? So if the two subsequences are of same length and they end at 3 and 9 till this much, which one do you think we should keep and which one do you think we should eliminate? Okay. And in fact, it turns out that we should actually eliminate this one, right? Why? Because if now there is a 9 value, right? Let's say there is a 6 after this. This 6 cannot extend this 9 because 6 is bigger than 9. But 6 can extend this 3, right? And it will give me a length of 4. But this will remain at length of 3. So if you have a smaller value at the end, you have more potential to expand its length, right? Because even like out of two values of the same length, something might be feasible with the smaller one, but it's not feasible with the larger one. So at any point in time, we have two subsequences which have the same length. Okay, we would ideally try to keep the one with the smaller ending value, right? That those subsequences would be more and more relevant. Okay, so that's something we kind of keep in mind as well. So the main thing that we kind of learn over here is, okay, if there is a P1, so the main representation for any particular element that we can try and see is, let's say there is a subsequence which is ending at 10, right? We didn't really care about the elements that were there, right? What we cared about was the length, that how many elements were there present over here, and what's the last element over here. Okay, so let's say we represent a particular sub-solution or a partial solution with what is the length and what is the last element, because these are the two key things that we're going to be seeing when you incrementally update with the new element, right? Because if you can extend the length, it will be possible to extend it with length plus 1. So in this case, we have this one, and we would love to compare with two things. One is like if last is same between two subsequences, keep The one with the higher length, right? If the last is same, we keep the one with the higher length. If length is same, keep the one with lower last, because the lesser the last value is, the more room for improvement the improvement in LIS is possible, right? These are two key observations that we kind of see over here, which kind of helps us to compare the partial solution. These are called partial solutions because they are still not the main solution, but they are like sub solutions that are currently getting generated while incrementally processing the thing. Okay. Next is storing this partial solution very, very efficiently. How do we store this up so that we can use it up, right? So let's go back. Over here we deducted that, okay, length is same. In that case, we keep the key as less than last value. So at any point in time when we are incrementally generating them, for length sem we have a fixed value, we have a one value, right? Only a single value. So the number of different valid subsequences that are there that we need to consider is actually going to be order n only, right? In fact, for every length there will be only one that is currently the best, and we have to keep track of only that. Okay. And for a single last, you'd be having a single length only. Okay. So for every length we have a single last. So there are many ways in which you can do this. The one neat way that we try to do this is let's say we have what is the last over here and what is the length. Okay. So what we keep over here is, let's say if you have processed till this much, okay. Okay. So one possible subsequence is, let's say this. Okay. So over here let's say for length 3, what is the best ending point that you can get? What is the best at last point? So I can potentially try and get for 3 a ending point of 6. How? This, right? What is the best ending point that you can get for, let's say 2? Okay. For 2, I can do at 5. I can end at 5, right? For 1, I can just do a single element of 1. That's the best ending point. Can I get 4 elements in this case? Yeah, we can, right? So the way we can get 4 elements is 1, 5, 7, maybe 9. The best ending point is 9. Okay. So we have 1. For 1 length, the best subsequence that we can generate till this point is 1. For 2 length, the best we can end at is 5. The 3 length for best we can end at 6. And 4 we can end at 9. Right? So this is how we can keep track. We note that for every length we have only one solution because it's the lowest last point, right? So this is what we want to keep track of. And since the lengths are incremental, we can try and store this one in an array, right? In some sort of array. Like let's say this is index 1, 2, 3, and we can try and keep 1, 5, 6 over here and 9 over here, something like this. Right? So this is one way in which you can store this partial solution efficiently in this case. So the main idea is to try and keep the partial solution over here. Now, right now we are kind of just thinking about this particular thing. How do we kind of maintain this efficiently? That's the main question. Okay. We did talk about that we can try and build this, but how do we maintain this efficiently? Okay. And there comes a main observation of this particular optimization. That is what we require for this one. Okay. Let's try to go forward and try to simulate a process and try and see. Okay. So right now we have an empty thing. We don't have any subsequence. 1, 2, 3, 4, 5, 6, 7. I'm just keeping it this much length. I don't think I will get anything more than this. So we are going to incrementally build. So when you have one element, you have only a single subsequence ending at 1 with of length 1. So this is the length. This is the last. What is the last ending point? Okay. Now when you get 5, right? So for 5, we can try and find which element can we extend. For 5, we can extend 1, right? So we're going to add 5 over here at 2 because there was a single length subsequence of ending at 1, and we can add 5 at the end of this. So 5 can be 2. Okay. Similarly, 7 can add at 5, 10 can add at the end of 7. Okay. So this is up till this particular point because these are the lengths that we will get. Obviously, like we can also do just 10, but only 1 is much better than just 10, right? So these would be on this side itself. Now comes in 9. Okay. So now for 9, what we see is 9 cannot extend, 9 cannot be placed over here. 9 cannot be placed over here, but it can be placed over here, right? Because it can extend 7 to a 9. So we can extend whatever subsequence was ending at 7 of length 3 with a 9. So we can get a 4 length subsequence with a 9. So we can replace this one with 9. Let's simulate this, and then I'm going to kind of quickly talk about what exactly is happening over here. So we can keep a 9 over here. Okay, let's say we processed up till this point. Next is 6. Okay, so we can see that 6 cannot extend anything in this direction in for the lengths 3 and 4, but we have a 5 which we can extend by a 6. We can have a 1 which we can extend by a 6, but everything on this side we cannot extend. Okay, so what we'll do is it wise to kind of extend just 1 with a 6 or 1 comma 5 with a 6, because ending point will be same. Note that the things that we consider about is last. Okay, so after extending, the last is going to be 6 only, but if you extend just 1, you will have a length 2. If you extend 1 5, you will have a length 3. So it's better to get higher lengths, as we observed. So we will always extend this one because it's always a valid state. So we'll extend with 6. So in that case, we will get a length 6 we will get length 3 and a 6 partial solution for this particular endpoint. And in fact, there was an endpoint of length 3 and last as 7. Note that since 6 is lesser than 7, it's much more better to keep 6 over here than 7, because 6 can maybe later on give us much more room to kind of expand over there, right? Okay, let's do 8. So 8 cannot extend 9, but it can extend 6. So we will extend 6 with 8, and 8 will be of length 4. We will replace this with 4. Okay, and then 9 can expand this 8, so we can get a 9 over here. And then we have a 2. So 2 cannot extend anything which ends with 5, 6, 8 or 9, but it can extend thing with 1. So what we'll do is, instead of this, we will go ahead and quickly just delete this one, and we will make it a 2. Okay, because now 2 can extend 1 and we're keeping it over here. Okay, for 3, what we are doing is we are kind of trying to keep track of which one can we extend. So the 2 we can extend with the 3, so we'll get a subsequence of length 3 for ending point at 3. So this is what we will do, and this is where we will kind of end at the end. Okay, this is how we kind of maintain it there. Now the neat idea over here is that this is always sorted, right? Because whenever you are inserting something, right, there's going to be a bunch of things which are like, let's say it is increasing. I'm going to just quickly prove it. Let's say there is an increasing set, 1, 2, 3, 4, something like this. Okay, something like this up till x. Let's say you get a value y. So since it's increasing, some of these values are not going to be valid, because we cannot extend these values. So these are all going to be greater than equal to y. Let's say there is this first element which is less than y. Okay, what we can do is that, and there are even lesser elements as well, but it's always optimal because the length over here is the highest. We can extend this with a single y with one more element. So this element will be replaced with an ending value of y. This is what we do over here in this particular structure. The reason being is everything over here was greater than equal to y. So if you replace y over here, it's always better, because earlier it was greater than equal to y. And we can actually place a y over here because the element over here was less than y. So it's like there is a subsequence of this length, of a length over here. So at a plus 1, we can get a subsequence of ending at y. So that's how we are maintaining this as a partial solution. In its true sense, what it's actually doing is actually building it up a tree. I'm going to show you that, but for now, let's understand this one. Okay, and then like if we have this like simple observation that we need to extend the one that is like kind of just less than y and put y over here, because it's kind of extending that one best. The simple thing that we can do next is actually to code this one. But where did we find the LIS, right? We can see that the LIS is actually over here itself. The best we found out was of length 5, so we can do it with, the LIS of this one is actually a 5 length subsequence. So what is the largest? Whatever largest length you get is what we keep. Note that we are keeping it in an array, but the main idea is to keep a length and last, and that's what we are maintaining, right? Since lengths can be up till order n, we can do it in a single array itself. Okay, great. So the way we're going to do that is we're going to code this one real quick, and I'm going to just explain the rest of the idea through code, and then we will talk about how we can kind of print it, or what's actually going behind the scenes, right? Let's try to quickly code this one. Okay, So let's say you are given the integer n, seen n, right? And integer ARR of n for integer I equal to 0, I is less than n, I plus plus, we are going to take the array, right? And we need to finally print this thing. So what we'll do is we will create a vector. Okay, we'll create a vector. Okay, named LIS. What we'll do is, so the vector is currently empty. Okay, what we'll do is we'll go through the elements in the array one by one. So this is like, now we are going to incrementally build the solution space, like whatever length, the last comma length that we can build till this ith index is what we're going to maintain in the vector LIS that I said. This vector is going to be nothing but this one, this thing over here, okay, that we were kind of drawing, this thing over here, this structure. But again, we're going to see some caveats over here. I understand that you might be thinking that how did this and some of these things came to my mind, or how these things kind of come up. It's actually a very, very standard classical idea. So you need to remember some of these things. It's not like possible to think of all of these things on your own, to be very honest. But still, I wanted to give you a clear picture on what is going on behind the scenes. So over here, we go through all the elements, and for the first element, for whichever element we are like currently dealing with, we're going to find out if it is bigger than the last element we had at the LIS. So at the start, LIS is going to be empty, right? It's empty. So if LIS dot empty or LIS dot back, which is the last element of LIS dot back is less than the current ARR of I. What is this actually talking about? If we have not found anything yet, okay, that's the first case, which means the first element is kind of coming in. The next thing is that even the largest element that we have seen till now, the largest ending, so LIS back is going to be give you the length, and the index is the kind of the value, and the index is the length. But whatever is the largest valued subsequence that you have seen ending at, even if this element is bigger than that, then we can extend the largest one, right? So what we'll do is we will LIS dot push back the current ARR of I. Okay, so we will extend this, or else what we'll do is we'll find out the first element. So note that the element that you can extend over here is like, which element can you extend? The last element that is less than y. So the element getting replaced is the first element greater than equal to y, and the first element greater than equal to y in a vector can be found out using something called as lower bound, right? So we can use a lower bound in this particular case. We quickly go back to the code. If this is not the case, then we can find out the iterator to the lower bound of LIS with the current element ARR of I. So find out the iterated to the first element that is strictly greater than equal to ARR of I. And what we said was we're going to place it over there itself. So it's going to replace it. So star of ID is going to be equal to ARR of I. This is what we're going to do. And if you just see out LIS.size, we're actually done with the whole problem to a certain sense. Okay, that's the whole LIS code. But it looks very cryptic, right? Let's try to kind of decipher it, what's going on behind the scenes. Or like, let's print out a few things. I'm going to print the LIS after every incremental thing. Okay. Let's run this up on a single example. Let's run this up on a single example. Okay, so I've copied down the input over here, and it's 10, 1, 7, 5, 7, 10, 9, 8. So this is the input. This is the array that we had in the slides. And let's quickly run it on this particular slide, on this particular input itself, and see what is happening behind the scenes. So let's close it off once. Okay. So when we process the 0th element, right, we have just like, this is the first element. So first is index 1. So we are actually doing it on a vector. instead of an array, and we're using 0 index, but actually we can think about it as an index shifted, right? So this is 0 index, but it will be like length 1. This is the first index, but it will behave like length 2. It is the third index, it will behave like length 3, and so on. So till the start, we have like 1 length subsequence ending at 1, 2 length subsequence ending at 5, 3 length subsequence ending at 7, 4 length subsequence ending at 10. But as soon as 9 comes in, we see that 9 is not bigger than 10, so we cannot even extend it even further, right, as a new element. But we need to find out where does 9 fit properly. So 9 at the best can extend the value 7, okay, because that's the first element strictly less than 9. And if you place 9 up after that, 7 was at index 3, or index 2 or length 3, 9 will be placed at index 3 or length 4. So 9 replaces the 10 because there was a subsequence which is ending at 10, but now you have a better subsequence of length 4 which is ending at 9. So we just replace it over here. Similarly, we see the like 6 over here, and when you see the 6, it's gonna be the 1,5 subsequence which it extends, and 1,5,6 is better than 1,5,7, so it replaces it. Okay. Then we replace 9 with 7 because like 6 can be extended with 7, and the same logic as 9 over here. Then we see a 9. Now the last element is 7, so we can extend it with a 9, right? Then we see a 2, so 2 get replaced over here because 1,2 is better than 1,5. 3 is added over here because 1,2,3 is possible, which is better than 1,2,6, right? So this is how we are doing, and we can obviously see that since we got 9 at the index 4, which is length 5, we are gonna have a LIS of length 5. So 5 is correct. Okay. So this is all there is to this code of LIS. This is a very, very short way to code this particular thing, and you can quickly check the time complexity as well. O of n. These are always order 1, but lower bound takes log n. So it is O of n log n, right? This is an n log n solution for finding LIS. Okay. But we found out a way to print the LIS. Sorry, just to print the length of the LIS. But what about printing the LIS? And some people, I think, have this misconception that, okay, this is going to give you the LIS as well. No, it's not, right? Let's go back and see. Is this the LIS at the end? Is this the LIS that you find out? No, right? That's not the best thing. We know that the LIS is going to end at 9. But is this the LIS? Obviously not, because 1, 2, 3 and then 7 is not feasible after that, right? So it's a partial solution. It's not actually the LIS. How do you find the LIS out of this? Okay. That's a really, really good problem to kind of think about. And I would actually encourage you guys to kind of pause over here and think about how do you actually make sure that this can be found out. How do we find out the actual LIS? Because things are getting replaced, and it's not like the newer sequence that gets created is actually present as a subsequence. This is a partial solution structure and not a subsequence always. Okay. So how do we find out the best possible thing in this case? That's the next thing that we will discuss. So we were talking about printing solutions, right? I hope you have given it a thought, and let's get into the main idea. So if we kind of try to analyze what was happening in the incremental solution, right? The way the solutions were getting like printed or like used in the structure was something like this. You had 1, then you extended it with 5, then you extended it with 7, then you extended it with 10, right? And then what we did, we got a 9. So we extended this 7 with a 9, right? And then we got a 6. So we extended this 5 with a 6, okay? Then we got a 8. So we extended 6 with a 8, right? Then we got a 9. So we extended 8 with a 9, right? Then we got a 2. So we extended 1 with a 2, okay? Then we got a 3. So we extended this with a 3. So this is the length 3. This is the length. This is going to be length 1, 2, 3, 4, 5, right? This is the diagram. And if you try to see what is happening behind the scenes, right, we're actually just getting the final array as the, if you see this particular structure from this side, whatever you're going to get is what you're finally getting over here. Okay. But this is what we had in the array. If you kind of quickly go back and see what we had printed over here, I think there was 7 over here instead of 8. Yeah, sorry. I think I like mistyped this one as 7, but it will be actually an 8. But anyways, that doesn't really bother us. This will be the final like LIS array that is going to be there. what do we think about from over here? So obviously the answer is going to be 5, okay, and the last value is 9. But to get the LIS, we have to actually channel back this way, right? That this is the actual LIS that is getting formed. Okay, we have to somehow channel this back. So for 9, we know it's present at 5. Okay, then whatever value for 4, we know that 8 is present at 4, right? 8 is present at 4. Then we need to find out the value at 3, at the length 3 in the subsequence, right? But it's not the last value that was inserted, right? It was the value, note this very, very carefully. It was the value that was present just before the 8 was inserted, like, or at the level of 8. When the 8 was inserted, what was the value at 3? Okay. So that was 6. When 6 was inserted, what was the value at 2? That is nothing but 5. When 5 was inserted, what was the value at 1? It was nothing but 1. Right? So this is what we are kind of interested in to find out. This is how we can try and go backwards. Okay. There are many ways to implement this. You can actually keep a back pointer and try to save which element is kind of getting inserted where and all. But I'm going to quickly show you one very, very simple way to do this. Okay. The way I generally do this is I'm going to just quickly find out another array, which is which element got inserted where. Okay. Inserted at, what is, where did this element get inserted at? Okay. So we are going through all the elements one by one. Okay. If the element was inserted at the end, we're gonna say that inserted at the element I was inserted at which particular index? It's going to be at the LIS.size -1. So if it's just, let's say, empty, so you're gonna get 0. It's gonna give you the index, right, which is present over here. Or you can like even keep it like this way. It depends upon how you want to implement, but this is what we are gonna doing. We are finding out where, at which index was this element inserted. Okay. Even over here we can find at the insert at for the element I that we are inserting. Okay, as like it is going to be inserted at the IT. So IT minus LIS.begin. And I'm just going to quickly drop this one over here. So which index it was, so which length it was inserted at, that's what we are finding out. So this is going to give us like 5 for the last one element. All the other elements it's going to calculate accordingly. Let's print out the final insert at array as well. Okay, so this is the inserted array, and let's try to give the same input real quick. Right. So see what happened over here. When you got 1, it got inserted at length 1. When you got 5, it got inserted at length 2. When you got 7, it got inserted at length 3. The 10 was inserted at length 4. The 9 was inserted at length 3. Is it 3? Think about it. So this is actually giving us the index, right? So I'm gonna, so IT minus LIS.begin is gonna give us the index where we are inserting it in the vector, and +1 is going to give us the length. I'm gonna keep the +1 length, or you can like equally like remove -1 from over here and +1. I mean insert a -1 and keep it this way as well. Both of them works. Okay. So now when you get 9, it replaces this 10 because it's better than 10 and it extends 7. So 9 was inserted at 4, 6 was inserted at 3, 7 was inserted at 4, 9 was inserted at 5, 2 was inserted at index 2, at length 2, and 3 was inserted at length 3. So this is like where for each element in this diagram, at which level was it inserted, at which level was it inserted. That's what we are finding out. Okay. Now, what are we looking at in this particular case if you have to print the LIS? Okay, so we know the length of LIS. So which length are we looking for currently is equal to LIS.length. Okay, LIS.size, the LIS length. So what we want to do is we want to go back to the last. So we have to go to the element which is present at the LIS length, right? Which element was at the last inserted at the current length of LIS, whatever is the current length, and we're gonna process it from the backwards. So over here we will see that, okay, let me go back and show you it in the array itself. Over here you can see that the first time something is present at 5, which is the length of LIS, is over here, which is nothing but the element 9, right? Now before this 5, what was the last element that was at 4? Nothing but 8, so nothing but 7. So we had extended 7 to a 9. Before this one, what was the last element at 3? It was 6. So this was the last element which was extended, okay? For 6, which was the last element which is present at length 2? 5. So 6 was created by the length 3 of 6 was created by extending 5 of length 2. For 2, what was the last one at 1? It was over here. For 1, what was the last one? We don't really have 1 because it's the final one, right? So the way we do this is we go backwards from the last. For integer I equal to n minus 1, you can say I minus minus, sorry, I is great. Okay, I've forgotten how to write loops now. If inserted at I, if the ith element was inserted at the current length, whichever LIS length we are currently finding, it is actually equal to 5 right now, okay? In that case, I'm going to print the LIS in a separate vector. Final LIS dot push back the current element, which is at index I, ARR of I, okay? And now we are looking at before this element, in the elements that were inserted before this, which element was inserted at curl length 1 less than this one, okay? Which element was inserted at 1 length less than this one? And then we incrementally keep doing this. At the end, since we are inserting the largest element at the last, we're going to reverse the array. We're going to reverse the final LIS, and we can now print the final LIS, let's say. Let's try to see this now. Okay, I forgot to add a semicolon, I guess. Right. So you can see, right, now we get this particular thing 1, 6, 7, 9, which is actually the correct LIS. It's not the final thing that is represented in the LIS array. It's the final LIS array which is getting created by going from the back and finding the first element which is insert, which was inserted at the last, which is the last element being shown over here, and it's actually the actually true end, okay? Before this element was inserted, what was the last element that was actually equal to that was actually present over here, and this element was created by extending that. That is what we are finding. So that is nothing but 7, then 6, then 5, then 1. So that's how this is kind of printing out. This is one way to kind of print this. You can also save while you're inserting maybe some back pointers and stuff. That will be difficult if you think about it, but this is a much more neater logic to print LIS in that case, okay? So this is almost all about LIS. I mean, this is mostly what you need to know about LIS in general. Like, how do you find out LIS using this code? I mean, even if you don't remember much of these things, even if you know how to like kind of just find out the LIS, that's more than enough at times. So this is for printing. So just quickly structure this code up for you. This is going to be like LIS.size is actually the length of the LIS. You don't even need anything more than this. Okay. But if you want to print things up, this is what you enable. And this is just printing stuff. So we go backwards and find out the final LIS and then reverse it up and print it up. This is how do you print the LIS if you want to. And inserted at is the index where the element was the length at which the element was inserted. Even if you do this one, it's not going to be a problem. It's just that you have to make sure that you start with current index in the array where you were inserted. So you will start with -1 and then proceed accordingly. Okay. So that's what we are kind of dealing with over here, and that's mostly the whole idea about LIS. So that's all the things that you need to know about LIS, right? And that's the best complexity. You cannot do better than nlogn for LIS, okay? So that's one good idea. Greedy plus binary search, sort of binary search is being used over lower bound, and the greedy ideas comes from this observation that it's always sorted, and we can do this, partial solutions can be reduced to this particular format, okay? That's all for this particular video. I think this is one of the most interesting application ideas of LIS, and like there are many more like use cases of LIS. One such thing that I'm going to give you as a quick task is find the longest Biotonic subsequence of an array. So what is a Biotonic subsequence? Something that increases and decreases. So first increase, then it, so there is an increasing pattern and then there is a decreasing pattern. So it decreases. Okay. So what we need to do is you need to find the longest Biotonic subsequence of an array. Okay. And it strictly increases and then strictly decreases. That a subsequence like that is called a Biotonic subsequence. And you have to do this in nlogn using whatever we have learned till now. And it's actually an extension of LIS only, but you have to think how you will apply it. And I can give you a hint for this particular problem, that can you find LIS ending at the index I? That is something that might be a key to this particular problem. Okay. So try out this particular problem. That will be all for this particular video. See you in the next one with another new problem. Okay. That's all. Bye-bye.